A confirmation about the audio, please, guys. If the audio is clear and available, kindly confirm. Thank you. So, hello, a very warm good morning to all of you, and welcome to Byju's Exam Prep IAS. Welcome to another session of geomorphology, where today we shall be initiating upon the discussion of volcanoes and other endogenic forces. So, when we talk about the portion of geomorphology that we covered yesterday, so yesterday we had talked about the aspect of creation of earthquakes, occurrence and causation of earthquakes, and why do these earthquakes occur. So there we had discussed that earthquakes basically can end up occurring because of variety of reasons. Now, we had also taken a look at the global distribution of earthquakes, the factors of induced seismicity, all those factors we had taken a look at. Now, today we shall be taking a look at volcanoes, their formation, their distribution, and their other properties as well. So here, audio is unavailable. Is the audio available to everyone? Kindly confirm. Yes, good. Thank you. So when we talk about volcanoes, these are basically some of the most picturesque and visually appealing features that you will come across in the entirety of the planet. And volcanic eruption on the planet is not a new phenomena. It is something which has been happening for a very, very long period of time. So let us understand what these are actually about. So overall, when we talk about the internal structure of the planet, we do know that in the layer immediately below lithosphere, you have the presence of asthenosphere. Okay, you have the presence of asthenosphere. And that basically is a weak layer below the lithosphere. Now we also know that in this region of asthenosphere, we have the production of heat, and high amount of heat is produced. What is the reason behind production of heat? The presence of radioactive materials and the decay of radioactive materials. So in this layer of asthenosphere, heat is produced by the decay radioactive materials. Okay, so by the decay of radioactive materials, that heat is produced. Now this heat many of the times generates a convection current on its own, right? So that can become, the asthenosphere can become a source of heat, and the heat generated could lead to a convection current which could rise up closer to the surface, puncture through the surface, and the molten materials can come out. Okay, the molten materials start coming out. So the vent from which these molten materials they come out, that is what is referred to as a volcano. So that is what we refer to as a volcano. So here, volcano is a vent. Vent means a passage, a pipeline in the Earth's crust through which heated materials consisting of gases, water, lava, and fragments of rocks are ejected from the interior to the surface. So here, when we talk about it, here, let's suppose you have this molten material. Vent means passage. You would have heard about the term bioventing or venting in terms of home ventilation. That is a vent. So here you have a pool of molten materials. That is what is referred to as magma chamber. Right? Now, from here, in this, you will always consist of or contain molten materials plus gases. Okay, molten materials plus gases. Now, gases are many of the times dissolved in the molten materials. When we talk about the gases, which are the major type of gases to be found, is basically you will find water vapor, H2O, sulfur dioxide, SO2, carbon dioxide, CO2. So these are the predominant gases which are present. And it is the presence of these gases which induce the pressure so that the molten materials can also be pulled up. So always it is the presence of gases which induces the pressure to be pulled out. Okay. So when we talk about the presence of gases, so the gases induce pressure to pull up the molten materials above the surface. That pressure is given by the presence of gases. So if you have large number of gases, molten materials along with the gases will be ejected. But sometimes what also happens, that sometimes these gases, they are not present in significant quantity. So in those situations, many of the times, despite the molten materials being present there, the molten materials are unable to come out because they lack the adequate amount or the required amount of pressure. So in that case, in those situations, those molten materials, they tend to remain in the magma chamber, and over a period of time, they start to solidify, right? Because over a period of time, cooling down will happen because they will give the heat to the surrounding regions as well. Heat will be dissipated to the surrounding regions as well. So that is where, in the absence of gases, when they start losing the pressure, they will start solidifying in this region itself. And that will lead to the formation of intrusive igneous rocks. Okay, so that is where you come across the intrusive volcanic landforms in general. Now, in certain cases, when the gases are present, depending upon what is the molten material which is available, because the type of magma, that also ends up varying. The broader classification of magma, which we will take a look at later on as well. So magma broadly is of two types. One is felsic, one is mafic. Felsic, rich in silica. Viscous. Viscous means does not flow easily, because here you will find the formation of silicate crystals. So generally felsic consists of quartz and feldspar. So both of them very rich in silica. So viscous means they will have a difficulty in flowing, right? Now, when the magma, let's say, has got difficulty in able to flow, slowly and steadily it lies there in one particular portion and in one particular state for a longer period of time. So that is when, let's suppose, the magma moves ever so slowly, rolls up over a particular region. There will be a greater penetration of air once that comes out. So let's say this magma has come out, or this magma here also, if it is coming out, and in this region of magma chamber also, it will not be able to flow easily. So the air mixture with this is much greater. So because of that, it is very low in density. Density is low. Okay. Whereas when we say mafic, very poor in silica. Poor in silica means it won't have those silicate crystals which were inhibiting the flow in the earlier case. So rich in iron and magnesium. Iron and magnesium. Viscosity, very low. That means it is almost fluidic. Is low. Now this is going to be having a higher density. Okay. So depending upon the type of magma that you have, accordingly you will have either an explosive eruption or a non-explosive eruption. Not all the volcanic eruptions that you will come across, not all of them are going to be explosive. So some of the eruptions, they happen very quietly as the molten materials, they start coming out. Now we have already seen that as soon as the molten materials, they come out of the surface, that is what we refer to as lava. As long as the molten materials are present inside the surface, that is referred to as magma. When it comes outside, okay, this is also molten magma or material. Now, the classification of volcanoes is done primarily on the frequency at which they are going to erupt. The frequency at which they are going to erupt, how frequently they are going to erupt, or what is the expectation of their eruption. So accordingly, the classification is done in terms of active, dormant, and extinct volcano. So when we say active volcanoes are those where the magma chamber is active enough, where the magma chamber is full, and there has been a frequent occurrences of eruption. Experience frequent eruption of volcanoes. Okay, they will end up experiencing a frequent eruption of volcanoes. Example of active volcanoes are many of them. When we talk about the example in India, you have the Barren Islands volcano. Barren Islands volcano in India. Okay, that is one of the examples. Now, other examples across the world, you can take the case of Tonga eruption, right? Hawaiian eruption. In Hawaii, you have three peaks. So Mauna Loa, Mauna Kea, these are the active ones in general. When we say dormant, has erupted a long time back, and there is a probability of a future eruption. That future eruption can happen, let's say, 50 years from now, 100 years from now, 500 years from now. But there's a possibility of eruption in future as well. Example, the very famous example of it is Vesuvius in Italy. And now Krakatau in the region of western part of Indonesia. In the region of Indonesia. These are a couple of examples. Now here you will find that the magma chamber becomes inactive for significant amount of time. The magma chamber is not active enough. And the presence of gas is very, very limited. There is no active formation of magma which has taken place for a long period of time in this case. So here we get an idea about the what is the status of magma chamber. How do we get an idea that whether the magma chamber is going to be full or whether it is full of gas, whether it is empty? How do we get an idea about it? Think about it. What can be the logical explanation that gives us an idea of what can be the tools or techniques which gives us an idea about what is the situation of the magma chamber? It is going to be the seismic waves, the study of the seismic waves. Many of the times, these seismic waves, when they travel, now you have the P waves being able to travel through solid, liquid, and gases as well. Whereas the S waves, they will be traveling only through the region of the solids. So, by the seismic waves, we get an idea about the situation of the magma chamber. What is the proportionality of solids? What is the proportionality of liquid? And how much gas is also present? Yes, Pinatubo is active. Pinatubo is one of the active volcanoes across the Western Pacific. And then we come across the inactive or the extinct volcano. So, extinct volcano eruption has happened a long time back. And there is no possibility of an eruption in future. So no possibility of an eruption happening again in future. So that is the case of extinct volcanoes. You have few of the extinct volcanoes across the globe, many of them. So over a period of time, when the eruption stops, that is when the erosion starts. And these volcanic mountains, they are reduced. Once upon a time, the mighty volcanic mountains as they would have been, now they get reduced into very smaller portions or remnant hills. When we talk about Mount Kilimanjaro, Now, Mount Kilimanjaro, for example, which is present in Africa across the region of the African Rift Valley. Now, Mount Kilimanjaro has got 3 peaks. Out of those, you have 2 peaks which are still said to be dormant, even though there has been an extinction close to around 2 lakh years before. One of the peak of Mount Kilimanjaro is considered to be extinct because in a kind of a recorded history, that eruption has not happened. So you have many such examples when you have, and why is it that they become extinct? There is no further supply of molten materials in that region. So the enrichment of the magma chamber doesn't happen. The magma chamber is very poor in terms of the availability of molten materials. And when you don't have the availability of molten materials, slowly and steadily the gases present that will also go away. And when you don't have gases, no molten materials, it will be extinct. Sometimes you have little molten materials but no gases, it starts solidifying. So as long as you don't have the continuous supply of molten materials, eventually a volcano can always go extinct. Okay. Now, this is the anatomy of a volcanic eruption. Here you will find that around the central portion, you have a volcanic vent. This is the vent. This is the volcanic vent. Now, what happens during an eruption is the presence of gases along with the presence of molten materials that pushes all the materials to emerge and erupt out of the surface. Example of extinct volcano, you can take the example as Mount Yeltsin, Mount Kenya also. Peak of Mount Kilimanjaro can also be taken as the example of it. You can take Mount Kenya. Then you will also have the condition of Mount Kilimanjaro. A peak of Mount Kilimanjaro, Mount Yeltsin. Okay, all these are examples of extinct volcano. Mount Fuji is not extinct. Mount Fuji is very much, it can be considered to be active also, in the sense that it has been erupting, but then there's a probability of future eruption as well. So Mount Fuji is nowhere extinct. Are they showing the characteristics of paleomagnetism? What is the characteristic of paleomagnetism? Paleomagnetism is a technique. It is not a feature to be exhibited. Paleomagnetism is a technique to study the age of the rocks based upon the magnetic properties of the rocks. That is paleomagnetism. It is not as if a rock will exhibit paleomagnetism. Okay. So here, what happens is that as these molten materials, they try to come out of the vent, many of the times the molten materials, they will come out as lava. But in the vent also, they will start to solidify. And that is where they will solidify in that entire region. They will form a kind of a very hard solid here. Now, when this solidification happens, that is what is also sometimes referred to as a lava plug. That is also what is referred to as a lava plug. Now here, these molten materials, sometimes they succeed in breaking through the surface, releasing a lot of gas. Now, out of the gases which are released, most dominant gas is water vapor. That is the most dominant gas to be found or to be released. Now, sometimes what happens is that it is unable to break through the surface because the surface has become so very hard. The surface has become so very hard that it is unable to break through. So it is in those regions or in those conditions that you will find that it starts spreading between the layers of the rocks. It will start spreading between the layers of the rocks and solidifying in the process. Maybe it will solidify here also. Okay. And that is how it is able to form very unique topographical features. That is the intrusive landform, the intrusive volcanic landform. Okay. Now, then after that, the reasons for the eruption of volcanoes. Now, generally, when you have the volcanic eruption, it occurs across the plate boundaries, and that too across certain specific plate boundaries. So generally the volcanic eruption happens across plate boundaries. And which plate boundaries? Here you have convergence, and in convergence you have a couple of them: ocean and ocean continent. Then after that, only in these cases will you have or will you experience the volcanic eruption. Then you have divergent, right? So divergent through the region of mid-oceanic ridges and few of the volcanic peaks, etc. You also have the eruption of volcanoes. Sometimes, in very rare cases, even across the region of transform plates. Very rarely across transform plates due to development of cracks. There are other regions also. For example, regions which we refer to as volcanic hotspot, which we will study later on, what we studied as the case of Reunion Island volcanic hotspot and so on. So very rarely across the transform plate movements also due to development of large cracks. Now, not always will there be a condition that if there's a development of a crack, there will be eruption of a volcano. No. Very rare circumstances, very rare conditions. And why? So, convergence and divergence, we know why volcanic eruption occurs. And we know that why only in these kind of convergences volcanic eruption will occur. We have seen earlier while we were taking a look at the plate tectonics that what is the reason why in the case of Himalayas we don't have volcanic eruption, and similarly in other continent collision also we will not have any volcanic eruption. So that is something that we have seen. What we have not seen is how is it that development of large fault lines or development of large cracks, how is it that they can initiate a volcanic eruption? Let us understand that. So here, when we talk about it, let's consider certain situations. Okay. Suppose this is the ground surface, and here, let's say you have a set of materials. Now, let's assume the temperature, surrounding temperature, let's say is 700 degrees Celsius. And here, the melting point of this material is considered to be, let's say, 750 degrees Celsius. So this material will not melt because the surrounding temperature is not as high as the melting point. Now, over a period of time, let's say because of various different geomorphic processes, there is a development of crack which takes place. A crack develops, right? Now, as there's or a fault line develops, anything. Now, as there's a development of a fault line or a crack, what will happen to the pressure exerted? So the pressure exerted on this material, let's consider this set of material as A. So the pressure exerted on A suddenly drops with the development of a crack. So basically what we have is pressure exerted suddenly reduces with the development of cracks. Now, when you have the development of or the cracks and faults and the pressure has reduced, now with the reduction of pressure, you also come across a kind of a reduction in terms of melting point. Now the material will melt much easily. So that is where you will observe melting point also reduces with the reduction in pressure. Okay. Melting point also reduces with the reduction in pressure. Always that happens. That is why when we talk about the inner core, it is unable to melt because the pressure is so high, the melting point will be much more higher as well. So that is where as soon as you release the pressure, as soon as there is no pressure which is acting, immediately the first thing that you experience is now the materials will start melting very easily. So as a result of that, let's suppose the melting point has reduced. And with the development of a fault line or a crack, let's suppose the melting point, which was earlier 750 degrees Celsius, let's assume that this melting point has reduces to, let's say, 680 degrees Celsius. Now, what do you think? Will the materials melt or not in this situation? What do you think? Yes, perfect. So here, the materials will start melting. Whatever gases have been present, they will also start bubbling up. And in these cases, all these molten materials along with the gases, they will rush to the surface. But sometimes the other thing can also happen. Let's suppose you have a particular region where, let's suppose we consider a set of material underground. Now, if the melting point might be 950 degrees Celsius, let's assume melting point in this case is, let's suppose, 950 degrees Celsius. And the surrounding temperature is, let's say, 700 degrees Celsius. So this will continue to stay in solid. It will not melt because the surrounding temperature is only 700 and this material requires a melting point of 950. Now, even if in this case, let's suppose a crack develops, a large network of crack or a fault line ends up developing. Now, as this crack or a fault line develops, there will be a reduction in pressure. That means a reduction in melting point. Let's suppose melting point reduces to 800 degrees Celsius. Now, here, after the removal of pressure, after the reduction of the melting point, still, what is the temperature? Temperature, or rather the temperature in the surrounding region is 700 degrees Celsius. The melting point has reduced to 800 degrees Celsius. So will this remain in solid or liquid? It will still remain in solid. Why? Because the melting point is higher. So in this case, no eruption takes place. Very good. So in this case, no eruption will take place. So only in rare situations will you come across a transform or a volcanic eruption happening through a vent developed because of a crack. And this will happen only in the case where the melting point is lower than the ambient surrounding temperature. Okay. If the reduced melting point is lower than the surrounding temperature, materials will melt and rise up. Here, let me add only. So, not in all the cases will you find this phenomena happening. This is only in the rare cases where the material also has got a melting point very close to the surrounding temperature, because many of the times you will have materials which have a melting point of, let's say, 1500 degrees Celsius. The surrounding temperature is 600 degrees Celsius. So regardless of the reduction in melting point, there is no condition or no possibility of that particular material melting up. So it is only in very rare circumstances that you will come across this phenomena exhibiting itself. Okay. Now, then we come across the type of volcanic landforms. And these are the classification of volcanic landforms based upon the eruption, the types of materials which are pushed out of a volcanic vent. So all of that distinguishes the different types of volcanic landform. So when we talk about volcanic landforms, you have the classification as cinder cones, composite volcanoes, which are very large, which are also referred to as stratovolcanoes. Then you have the shield volcanoes, and then you also have the lava domes. These are the basic kind of landforms. We also have a kind of a fissure eruption that we saw in the case of plate tectonics, and we also have the case of a caldera. So that is something we'll take a look at it after this. So here, when we talk about cinder cones, so what are these? Cinder cones generally, the term cinder is generally associated in English with anything which is very hot. So you have a typical conical volcanic landform which is created where a lot of these cinder balls, they are thrown up into the atmosphere. The small lava balls that are present here, sometimes you will have the presence of basaltic lava. It will come out from a central vent, and that central vent, the materials will rise up along with many of the solid particles, and they will then be dropped on the conical region itself. So normally, if let's say you have this particular region as the vent, normally, let's say this is the vent. Now if the molten materials, they start to come out, these molten materials along with some solidified portion of lava, which in a way solidifies as it comes out, now it will get emerged or erupted with a certain amount of force, and all those solid accumulants will drop around. Over a period of time, you have development of a kind of a conical structure, right? And that is what we have as the formation of a cinder cone. Generally, whenever you talk about a volcanic eruption, majority of the volcanoes across the world will have a kind of a crater on top, right? What is also referred to as a volcanic crater. So when you talk about a volcanic eruption like this, let's suppose, it will generally end up having a crater on top. Now, this is the volcanic vent. This is the magma chamber. Now, this crater, that oftentimes is the pool of molten materials that you come across in the case of active volcanoes. When the volcano becomes extinct, it is here that you will find that water comes in, accumulated rainwater, streams, etc., and that forms a crater lake as well. Now, in this situation, when we talk about the volcanic vent, you have to understand that whenever there is an eruption, this is the vent. Whenever we come across an eruption, now that eruption basically means that you have lava which comes out, and some lava will be molten material will be here as well. Some lava or molten material will be here as well. This will solidify, right? So this will solidify, solidifies to a hard substance. Now, for the next time that the molten materials have to come up, next time that the eruption has to happen, this solidified portion has to be cracked. This solidified portion has to be broken. And for that, you require a very high amount of force, always, right? So basically, you will have significant amount of force which is required. And it is that force where the magma starts pushing up against these solidified portions. That is when it cracks open. Many of the times the land develops a large crack, and this leads to a volcano associated earthquake as well. Okay, so that is basically what leads to an earthquake. Many of the times when it is finally broken, immediately as the eruption starts, you will observe very black smoke, and a lot of these solid particles, they will also be thrown up into the sky, right? And here, when it is thrown up into the sky, it drops nearby. And after all these wastage materials or the blocked solidified portions have been removed, that is when the remainder portion of magma starts oozing out or starts coming out. But nonetheless, it is a very violent event where this plug is broken. So let us take a look at each one of them and let us try to understand their individual features. Okay? Who invented volcano? I hope we understand the difference between volcano, between discovery and invention. So, invention is something that you design on your own, and discovery is something that you find it, which has been happening for a long time. So, nobody invented Mount Everest. Somebody discovered Mount Everest. Nobody discovered a refrigerator. Somebody invented a refrigerator. So that difference is something which should be understood. Volcanoes could never have been invented. Okay. And I don't think we have recorded history about that, that when, for what was the first time that a human would have seen the case of a volcano. And is this question significant for UPSC? Absolutely not. Not even close to what UPSC asks. So get a look at some of the previous year questions of UPSC just to gain an idea that what are the types of questions that UPSC asks. Okay. So that is always advisable. So here, when we talk about these cinder cone volcanoes basically here, they are not very great in height. They generally will be around few hundred meters tall itself. They are not the tallest of the volcanoes that you will find. So here, 1,000 feet above their surrounding. So they rarely grow larger than 1,000 feet above their surrounding. Here you observe that this is the solidified portion. This is the solidified portion of the volcanic vent. This is the crater. Now, for the next eruption to happen, this has to be broken, this has to be dismantled, and then it has to be thrown up into the sky. And if, let's say, it doesn't have enough amount of pressure, the magma doesn't have enough amount of gas, then there will never be enough pressure to break through, and the magma will remain trapped inside. It will solidify in the interior only. So they occur when particles and blobs of lava are ejected from the volcanic vent. The lava is blown violently into the air, and the pieces they rain down along the vent. And that is where the pieces they tend to accumulate up. And as they are accumulating, that is when they will be able to form a kind of a conical structure, a kind of a conical uprise. So over the time, this builds up a circular or oval shaped cone with a bowl shaped crater on top. Okay. So blobs of lava means masses. Blobs are basically masses of lava containing gases as well. So sometimes when you have, think about it, that you have a lot of bubbles which are released into the air. So they are chunks. So anything that you expect, not bubbles exactly, but anything which exists as large chunks, that is blob. Yes, globules, modules. So here, that is the cinder cone. Amongst all of these, the earlier ones that we have seen, amongst all of these, other than lava domes, obviously, these are the smallest in size. Composite and shield volcanoes are much larger in terms of the size of it. So when we talk about composite volcanoes, these are what are also referred to as stratovolcanoes. Stratovolcanoes. They can extend hundreds and, in fact, thousands of meters above sea level. So these are some of the largest volcanic landforms created on the land surface. So this is where they can be very, very extensive. They also end up gaining a typical conical shape in general. Here also you'll find a conical shape which is developed. So here, stratovolcanoes. So the name strato is derived from the term strata. So here that means there is a kind of a layering. So that means you have presence of layers. Okay, we don't have an idea about sea level. Okay. So how do you measure height of a particular region? When you say the height of Everest is 8,848 meters, as compared to what? As compared to Lucknow, Patna, or Delhi, or Kathmandu. When we say that, let's say, Mariana Trench is almost 11 kilometers deep, As compared to what? As compared to the top of the Mount Everest, as compared to the building that I live in, or as compared to your office? How do you compare height, or how do you give an idea about the height in general? Anywhere across the planet, if you have to give the idea of height. So have you ever thought about it? So always the point of reference is considered to be the sea level, because the sea level, or what is also regarded as the mean sea level across the planet, that is consistent. I hope we are aware of this fact. It is not going to be the case that Atlantic Ocean has got much higher level of water than the Indian Ocean, and Indian Ocean has got a lower level of water because there are poorer countries around. That is not how it works. So basically, the entirety of the planet, water is interconnected. The portion of at least oceanic water is interconnected. So the level of water, that is regarded as a point of reference. And that is where we get the objective of mean sea level. Mean sea level is used to measure height. Whenever you have traveled by railways, if ever you have noticed on the station, right, that is why you have to be very well aware and involved about your day-to-day lives. Right, generally when we have a lot of people who travel by the railways, and the attention is when to sleep, when to eat, what to eat, where is my destination, that's it. But if you ever have taken a look at the station board, that will have a kind of a reading. Every station board in the country will have a reading that the altitude is XYZ meter above mean sea level, right? So I hope now we get an idea. Mean sea level is the kind of height. Okay. Yes, everywhere it is written. You go to a new place, you go to any particular region, there also it is written. As you enter a particular district, the district board, that will also write it. Okay. So we had a couple of people who were asking about sea level. So I hope that sea level is clear. Good. So now here, okay. So now we come to the stratovolcanoes. Now there you will find the presence of layers. Layers of what? Layers of solidified molten materials, layers of ash deposited on top of it, another future eruption creating a layer of molten materials on top of them that have solidified. So all of this eventually, slowly and steadily, builds up the entire layering of the structure. And it can grow very tall and very wide as well. Not as wide as a shield volcano, but it can grow significantly wider, and it can grow very, very tall. The tallest of the volcanic peaks across the globe that you come across, they are stratovolcanoes, the tallest of them. The most predominant or the prominent of them, they are going to be stratovolcanoes. That means they are going to have layers within them. So that is basically the condition of stratovolcanoes. Now here, over a period of time, what happens is that the development of layers, etc., which continues to happen, the stratovolcanoes, they become very tall, very hardened, very tough around the region of the volcanic vent. It is no longer possible for the molten materials to be able to crack through the volcanic vent, because everything will solidify as well. Everything will solidify after an eruption. Maybe after 10,000 years, or maybe even after, let's say, 500 years, there is another eruption which has to happen. Now, when another eruption is supposed to happen here, let's suppose now these all the thousands of meters of solidified material has to be broken off, has to be removed. That will require a lot of pressure. Many of the times the gases will not have that much pressure. So as the molten materials along with the gases, they try to come out, sometimes they will find, due to the multiple attempts that they make, they will find the presence of certain cracks or weaker portions across this structure. let's suppose there is development of a kind of a weaker structure. Now, wherever there is a weaker structure or crack, immediately molten materials along with the gases, they will rush out of it. They will start rushing out. And when they rush out of it, that is where you have another eruption, that is not from the central vent. This is not happening from the central vent, far away from the central vent, but on the sides of it. And it is connected to the same magma chamber. So the molten material here is being supplied from the same magma chamber. These are what are referred to as parasitic cones. These are referred to as parasitic eruptions or parasitic cones. Just like a parasite is dependent on the host body organism for the availability of food and so on. Parasite is always dependent on the host organism. So here when we say or when we talk about parasitic volcanoes or the parasitic cones, they are supplied from the same magma chamber but emerge out of the weaker cracks on the sides of the main volcano. So example, you have Mount Shasta as a composite volcano, right? And then where is Mount Shasta, by the way? It is situated in the western parts of North America. That is where you have the presence of Mount Shasta. And you have Shastina, which is a parasitic cone for this. Mount Fuji is a composite volcano. Okay. Then, for example, even Mount Vesuvius that you have, Stromboli, all of these are composite volcanoes in general. Cotopaxi in the region of Ecuador. So that is also a condition of a stratovolcano. All of the major ones that you will find. Cotopaxi is in fact one of the only volcanic peaks around the region of equator to be covered with snow. So that is a unique feature of Cotopaxi present in South America around equatorial area. So that is basically the case of composite volcano. Understand that you have the presence of layering and the presence of layers due to deposits of the molten material, solidification of the molten material, and deposits of ash content on top. Solidification of molten material and deposit of ash on top. Can this threaten lives in nearby area? Absolutely yes. Absolutely yes. It can threaten the lives in a large area. For example, I think you have not read about the very famous story, which is generally included in English literature. That is why. So in English literature, you have a very famous story about Vesuvius and the eruption of Vesuvius. Now, Vesuvius, for a long period of time, even in the ancient Roman Empire, it was thought to be an extinct volcano, that there is nothing which is going to happen there. Then, suddenly, there was an eruption around 78 AD. And that eruption was recorded significantly because the entire city of Pompeii, that was consumed by the lava. Many people died. So, for a long period of time thereafter, people were very afraid to go near Vesuvius. Various mythological facts and stories developed that if you go near Vesuvius, this will happen, that will happen, and so on. So people would not even settle down near Vesuvius. 50 years passed, no eruption. 100 years passed, no eruption. 200 years passed, no eruption. 500 years passed. Those stories, they started turning into myths, folklore, bedtime stories, eventually turned into legends. 1,000 years passed, no eruption. So again, there was a well settled city which developed around Vesuvius. But again, around 1500 years later, there was another massive eruption. And then, when that massive eruption happened again, that is where, again, all the settled areas around, they were completely devastated and consumed. So whenever you have a volcanic eruption, a lot of lives and properties are basically consumed in the nearby area. Is it necessary to make diagram of these volcanoes? Absolutely yes. Absolutely yes. But please don't start making the diagram of volcanoes if a question is for earthquakes. So obviously, looking at the demand of the question, you have to draw the diagram. But in geography answer, please don't even dare to dream of an answer which doesn't have the diagram. Your diagram should be present. Okay. Parasitic cones basically are the ones that you will find where from the central point they are unable to come out. So the molten material. So this is generally found only in the case of stratovolcanoes because they are the only ones which are extensive enough, which are so large enough. Composite volcanoes are always active, not always so. Why will they always be active? Composite volcano is the landform created. So active or dormancy or extinction is dependent upon the property of the magma chamber. It is not dependent upon the shape of the cone above. Why we call them stratovolcano? Because you have the development of a kind of a layering. That is why. The strato. So strato is derived from the term strata. Strata basically refers to existence of layers. You would have read it in your editorials and English language also. Various strata of society, all of them are impacted by rupees 2000 note, etc. So that is where strata word is used. Okay. Do they ask types of volcanoes? They ask different types of questions about it. We'll talk about it. And is Mount Kilimanjaro a composite volcano? Yes, it is a stratovolcano. Yes. Okay. What is ash cloud? Ash cloud basically, Kishan, what we had seen earlier. This. This is what is an ash cloud. Now here, lot of these materials will be, see, when we say molten materials are coming out, which are these molten materials? What is consisted in these molten materials? They will consider or they will consist of many of the different rocks and rocky substance which are melted down, which are burnt. So there, by that process of burning, you will have presence of ash as well, formation of ash content as well. So along with the gases, they are also expelled into the air. That is what you have as ash cloud. You have small particulate matter also of the solidified lava vent, which is also thrown upward. So that is also ash content. Okay. Any question come related to Russian volcanic eruption? No. UPSC is not regionalistic in terms of. So UPSC had asked a question. I'll tell you, last year UPSC had asked a question. In fact, not last year, year before that, UPSC had asked a direct question that 2021 has been a year of multiple volcanic eruptions. Recount the major volcanic eruptions happening across the world, along with the reasons. So there, UPSC did not expect you to recount all the 41 eruptions which happened, but you should be able to point out that what is the kind of eruption happening in Iceland, what is the kind of eruption happening in Canary, what is the kind of eruption happening in Tonga, where else you have the eruptions which have been observed. So these kinds of questions are always asked. Crater and vent are not the same. Vent leads to the formation of a crater. Okay. Now, then we come across shield volcanoes. These are by far the most extensive and the largest of the landforms created during a volcanic eruption. These are very extensive, very, very large. Now, the name shield is taken from the ancient battlefield shields that you would have. Now, those shields that you would have in the ancient battlefields, they would have a very kind of a plain feature. slight bulge, but a very kind of a plain featureless kind of a condition. So that is the shape which is observed here. That is why the shield volcano. Now this shield volcano, it will consist of fluidic lava always, regardless of where it is erupting. If you have the formation of a shield volcano, it will be fluidic lava. And why? Because it is only the fluidic lava which can spread over to a large extent to be able to develop a kind of a shield in return of it. So that is what you will find in this case. Always development and existence of a fluidic lava. So here, fluidic basaltic lava flow. They can extend for thousands of meters, right? Thousands of meters in terms of their height. They can extend for thousands of meters above sea level. Again, I hope we are now understanding what is sea level. So here, that can be their height and their extensiveness. And in width, again, they can cover thousands of square kilometers of area. So you have various different shields across the globe. In India, if you take the example of shield, so in India, the example will be Deccan traps. The Deccan traps that you have, or rather than Deccan traps, I will introduce you to the term traps much later. So here, think about it as Deccan shield. You have Canadian shield. So that is where a lot of fluidic lava flow happens. And it will slowly and steadily spread over a very large area and they solidify. So many of the time, for example, if we talk about the Deccan region of India, you will find that there are kilometer thick deposits of lava. Now, that has not happened once or at one go. That has taken multiple different thousands of years and millions of years to form that thick lava flow. So that is where these shields are to be found in many parts of the world, and they form very large areas. Even in Africa, you have a large shield. So these are to be found. Now, whenever you have, let's say, fluidic lava which comes out, fluidic lava means is able to flow easily. Now, in that case, do you think there will be an explosive eruption? Or do you think that lava will come out in the case of non-explosive eruption also? What do you think? When you have fluidic lava, do you think there will be an explosive eruption involved or a non-explosive eruption will also do? Beautiful. It will be non-explosive because here the materials are able to flow very easily. They don't require an explosion to happen. So oftentimes you will find effusive eruptions, basically meaning non-explosive eruptions. Okay, that is referred to as non-explosive eruption. Now, this is also what is observed in the region of Hawaii. So that is why many of the times you have the reference as Hawaiian eruption as well. That is something that you find in the case of shield volcanoes. Many of the times also referred to as Hawaiian eruption. Okay, so that is something that you observe there. Then we have the smallest of all these features, that is a lava dome. Now, lava dome is consistent of very viscous lava that is unable to flow at all, very highly viscous, Viscous means very sticky in nature. It doesn't have the ability to flow. So that is when we talk about the viscous lava. Immediately after coming out of the vent, let's say this is the vent. Here only it will solidify. Here only it will solidify. And then, because it is very, very viscous, it will not end up flowing. It will not end up flowing significantly. It will solidify. Observe here. It has solidified here only. Right? Now, slowly and steadily, let's suppose 50 years from now, there is another set of molten materials which try to come up. Now, because the solidification has happened, these molten materials, they should start coming up. So the expansion happens from inside. It simply ends up getting inflated. Many of the times you will find these lava domes created at the vent of a stratovolcano also, blocking the stratovolcano's exit, right? So this is to be found in very small height and very small physical profile. That is very, very small. So many of the times can be formed on top of the vent of stratovolcano. Domes grow from inside out as newer materials are pushed through the surface. Okay? Etisha, you have told that these shield volcanoes present near to sea level. Where did I say it is present near to sea level? Please don't take sea level so seriously, my dear friends. When did I say that shield volcano is present near sea level? Shield volcano can be present anywhere. Deccan Shield, is it present near sea level? Deccan Shield has got significant amount of height. But nonetheless, you have a long question. So you have told that these shield volcanoes present near to the sea level. But it is given it became explosive if water get into it, which means can we conclude that there is always eruption in shield volcanoes? Where is it given, first of all? Please don't intermix five different concepts. As of now, kindly just concentrate on the class. How many of us have that very good and virtuous habit of having a book, textbook on the side, looking at the sessions and having a note copy on the other side, so that we will simultaneously end up grasping what is there in the book, what is there in the session, we'll make the notes, and we are ready for the mains exam in 2 days. How many of us have got that ability and the skill? So all of us who have got that ability, kindly for a brief moment of this 1 month for this subject, kindly change that habit, because here we are not going to pursue the portions which are given directly in the book. Has UPSC told you that this is the book, this is the course book? Has UPSC mentioned that this is the course book from which I will ask questions? No. Then how come you are dependent so much that this is the book, I have to match what is given here, and then I have to? But nonetheless, whatever is your approach, please kindly don't end up mixing and matching, because in that way none of the concepts will get clear. You will get so murkied by the level of it, and I'm not going to repeat what is given in the book. So the basic expectation that you have from the session, let me make it absolutely clear. If you are looking for someone who is going to repeat exactly what is given in the book, On Amazon, you have audiobooks which are available. That whatever is the text given, somebody will translate that, will keep on dictating. You can get your AirPods on, you can have a nice sleep over it. So the reason that you are attending the live sessions is to be able to gain a perspective, not a translation of the book. Having said that, coming to the basic question that you have asked about the shield volcano. Shield volcanoes can happen anywhere, everywhere, depending upon the availability of lava and magma. Later on, we will study that it is the volcanic hotspots which supply the molten materials into the magma chamber in the case of shield volcano. The Deccan Trap volcanoes that I am talking about, that did not happen when India was in its present state. That happened around 90 million years back when India was still very much in the southern Indian Ocean. The Hawaiian shield that you have, that is not because of some random eruption that is happening. There, the magma chamber is continuously being supplied by the molten materials from the inner portion of the mantle, from the region of Gutenberg discontinuity, that is the core mantle boundary. From there, you have the molten materials being supplied over to the region of Hawaii. That is where you have the creation of the shield. So there is no kind of correlation between occurrence of a shield volcano, no correlation between the shield volcano and the sea level. Okay, don't take sea level to be so seriously. Sea level is just a kind of a reference point. Okay. And for the session of geography, I would suggest to you attend these sessions first, revise it with the level of books. Trust us at least to this extent that we will not start telling you that India, India was directly taken from Mars and implanted on the planet Earth. And that is why we have such beautiful country. So at least cover the entirety of 24 modules. Trust me. After that, covering the portion in the book becomes very, very easy. On a daily basis, what you can do is after the class, you can take a look at the book. But if you are simultaneously reading it, that is why I am facing or I am getting these kind of questions where I have talked about a particular concept, I have repeated a concept, and then I have the same candidate asking me the question that, what did you say? I just missed it out. So obviously, you are looking at something else at that point of time. So please don't do it. So a lava dome's pulkit is basically when you have a lava dome. This is where you have very viscous materials coming out of the vent and immediately solidifying. That is where we have the lava dome. And it is a very small feature. Can we say basalt is converting into andesite? No, not always. Basalt, when you have a kind of a granitic eruption, that always gets converted into andesite. Anjali. Okay. Lakshmi, in how many days geomorphology will get completed? Depends. Depends on how quickly are we able to grasp the concept and how quickly are we able to follow. If we have the set of questions that we are facing, then it will take a longer period of time. But if we have a better level of understanding, it will be completed earlier as well. Okay. Now, I hope we are not in a hurry to finish geomorphology, enter into climatology, enter into oceanography. So just have patience. Whatever portion is being taught, follow that, understand that, your job will be done. Trust us. So now we come across fissure volcano. When we say a fissure volcano basically is when you have development of a large fissure or a large crack. So when you have a large fissure or a large crack which opens up, that is where a lot of molten materials they get spread around. A lot of molten materials they get spread around from here. For example, when we had the very famous Laki eruption in Iceland, which erupted around 1770s in Iceland, which erupted around 1770s. So this Laki eruption when it happened, you had a 37-kilometer long crack which opened up on the ground surface. 37-kilometer long. And that is where this is the image of the Laki eruption. So there you had the molten materials which started coming out. Many thousands of kilometer cube of molten materials, they came out, they solidified. Now this fissure eruption will be observed generally where? Wherever you have the divergent plate boundary. Divergent plate boundary. So wherever we have the divergent plate boundary at the points of divergence, that is where we come across fissure type of volcanoes. This is very easily observed in Iceland. That is why this is also what is referred to as Icelandic eruption. Icelandic eruption. Okay. So here, for example, they are formed, here observe, low viscous magma. That is the basaltic, felsic magma. That starts coming out along a long fracture and a fissure, and the resultant is spread over the ground surface. And that is what is referred to as Icelandic type of eruption. Then after that, we will come across calderas, but before that, we'll take a break and then we will be back. Stratovolcanoes are always felsic? No. Pulkit, no. Stratovolcanoes can be basic or can be basaltic as well. Ravendra, can lava domes be formed over shield volcanoes? Generally not, because in the region where you have shield volcanoes, you have fluidic materials, fluidic magma. And for lava domes, you need viscous magma. Fissure volcanoes are found at the region of divergence. Wherever there is divergence happening, there will be a fissure volcano. For example, here, if you take the case of Laki eruption of Iceland. So Iceland is one of those. Then you have Travera eruption in the region of New Zealand. That is also an example of fissure eruption. Okay. Is that understood? So we take a break, 15 minutes, and then we are back. Divergent is when the plates are moving away. That is divergent. Take a look. Excuse me. Take a look at the recordings of plate tectonics. You will understand. Madhur, mantle plumes will do. We will do. Acha, is that a question? Yes, we will do mantle plumes. Yes. A confirmation about the audio, please. If the audio is clear and available, kindly confirm. Thank you. Uh, Anjali, is it important to remember that which country is ahead or before GMT? Just a broader understanding of where a particular country is, that is also more than sufficient, right? A broader understanding that if we have a particular country to the west of prime meridian, it will be behind GMT, and if it is to the east, it will be ahead of GMT, but such questions are not asked. Okay, right? Why is there no significant upliftment in the case of fissure volcanoes? So when you have a fissure volcano, see why a fissure volcano happens. Fissure volcano happens or ends up getting created when you have two different plates. Let's suppose you have two different plates. Okay, let's suppose. Now these two different plates, they are going to move away from each other due to the convection current. So in the case of divergence of plates, this is something which is observed. Now here sometimes as the movement is happening, the molten materials, they will try to come up from here, they will try to come up from here in these areas, and they will start spreading over. So here they will start adding material, forming a thicker layer of the crust. So you won't find a kind of a peak like, even if a peak like formation happens, that is not going to be very extensive. This is going to be a smaller one. Because what is the meaning of fissure here? Fissure is a large crack. Okay, so when a large crack happens, materials will start to spread over rather than accumulating. Had this been a kind of, let's say, non-fluidic or viscous material, it would have accumulated. But here you don't have that kind, you have fluidic magma which is present, so that is why it spreads around very easily. Distinction between the types of magma, we'll come to it, Alok, don't worry. We'll talk about the chemical characteristics of magma. We'll come to it again. Okay. And one question by, can you explain deep about fissure volcanoes? Okay. So fissure volcanoes, I hope now it is understood, Sanjay, or I hope the doubt doesn't persist anymore. Fissure volcano happens when you have a development of a large crack and a fluidic magma spreads out, or a fluidic lava spreads out. Then we have the creation of a caldera. Now, calderas, these are very unique landforms which you will come across in generally in the case where the volcano simply subsides or caves in. So let us understand the formation, how it happens, why it happens, and in which areas we observe this. Why this fissure volcano called fissure volcano? Because it is happening across a fissure. See, fissure is the English terminology for cracks, large cracks. So rather than from a central vent, you have a large crack where there is upwelling of magma. So magma is getting upwelled from a very large area. That is why it spreads over. That is why this large crack is referred to as a fissure. Fissure, the English meaning of fissure is crack. In geography, I would again suggest to you, even in certain cases where we are unable to understand the geographical connotation of it, just the English translation of it is, if it is understood, many of the geographical phenomena will be easily understood. So look at the English meaning of it. Now we come to calderas. Now, how is it that calderas get created and why do they get created? So first of all, calderas will get created whenever you have very intense or very explosive eruption. Very explosive eruption. So they are, first of all, resultant of very explosive eruption. So let's suppose you have a large stratovolcano. Let's suppose you have the presence of a very large stratovolcano having a crater on top. Now, this large stratovolcano will obviously be connected to a very distinctly large magma chamber, and observe this entire process very carefully. So here it will be connected to a magma chamber also. A large magma chamber will be connected to it. Now, when you have a significantly explosive eruption, in those stages of eruption, when let's say the magma chamber gets emptied, right? Magma chamber can get emptied. The molten materials, it is not as if always they will be supplied. So when the molten materials are not supplied anymore and there is an explosive eruption, magma chamber gets emptied. So the magma chamber has gotten emptied and there is a very explosive eruption which has occurred. So when there is that explosive of an eruption, explosion of an eruption which occurs, this particular landform will develop cracks all around. Weaker points will develop a large crack all around. Now, eventually, this is observed, the formation of a caldera is observed when the magma chamber becomes empty. Magma chamber becomes empty. Now, when the magma chamber has gotten emptied, then you have a vacant space here. In the region of the magma chamber, you have a vacant space. Vacant magma chamber. Okay. Now, when you have the vacant magma chamber, there is a lot of weight which is applied from top. All this will apply a lot of weight on top. So as a result of that, the land will simply collapse. It will cave in. It will subside because there is nothing holding that weight. This is a vacant space in the region of magma chamber. So imagine if you have a very tall building and underneath that building, the ground is becoming empty, right? So what will happen to the building? The building will collapse. So due to the weight imposed by the overlying volcanic landform, there is a kind of a subsidence, a caving in, a collapse which happens. And when that collapse happens, that is when the top portion simply caves in. And when this top portion caves in, it forms a very large opening or a pool of sorts later on to be filled with water from the nearby seas, from the nearby oceans, if they are happening in that region, or development of a large lake also gets created in this process. So this is what we refer to as caldera. Okay, so very explosive eruption, magma chamber becomes empty, and after that, the weight of the upper portion leads to a collapse. And subsidence. As a result of this, you have a central depression which is created. So imagine the image that you see here. Imagine that at one point of time, this would have been a very tall stratovolcanic mountain. Now, the top portion has collapsed, and then eventually, because generally such kind of explosive eruptions are observed near the sea, near the water bodies, large water bodies, because when you have water penetrating into the region of magma chamber, that is when you have a lot of steam which is produced, lot of pressure which is added, and there is a significant amount of explosive eruption which follows. So that is where in many of the cases seawater gets in. And for example, if you talk about various different calderas created, for example, if you talk about Crete in Greece, that is also a caldera, right? Crete in Greece, that is also a caldera, right? So this is basically that recently, that is in January 2022, we had the eruption of Tonga eruption in the case of Pacific. Now, in the region of Tonga eruption of Pacific, the Tonga Islands around Pacific, you had two volcanic peaks. You had Hunga Tonga and Hunga Hapai. Now, you had a continuous eruption happening all the way from around December 2021 all the way around 15th of January 2022, where both of these were erupting simultaneously. And the final stages of eruption, when the magma chamber was finally emptied, it was a very explosive eruption, one of the most explosive eruption in the past couple of decades, so to say. And the entire region, due to that explosion, it simply caved in because the magma chamber was also emptied. Does not mean the magma chamber will never get active again. It might again get the supply of molten materials, can get active again, but then it has been emptied. Now, when it is emptied, in that case or in that situation, what happens as a result of that? As a result of that, the top portion, the weight of it simply collapses. So that is basically the formation of calderas. So once you have the formation, seawater gets in, or in many of the cases, rainwater keeps on accumulating, groundwater from the surrounding region also seeps in, forming a very large caldera lake also in the process. For example, around the region of Oregon in US, that is also where you have caldera. Now, even in India, we find the evidences of ancient calderas around the region of the northern part of the Aravalli ranges, which indicates a very ancient volcanism, which would have happened many, many million years ago. So that those calderas generally are observed wherever you have the conditions or the formation of a stratovolcano. This collapsing happens, yes, that collapsing happens immediately after eruption. Okay, so that collapse will happen immediately after eruption because that violent eruption will lead to development of cracks. This leads to development of cracks. Okay, so that is the factor of caldera. Then we come across what is referred to as mantle plumes. So when you hear about the term plumes, what is the first thing that you gather? What do we understand by plumes in general? Let me see. Any of us, we know the meaning of plumes? What do we understand when we talk about plume? A cloud-like structure, not exactly so. Yes, Pratham. Something coming up. That is better. Very high temperature flames, a correct column of heat, that is also correct. Okay, it is basically sort of a rising column. So whenever you, let's say you observe a fire on the ground surface. Now that fire, if you observe the smoke, how it rises, it basically doesn't, the smoke will not start rising all around, and it will follow a kind of a verticality, a rise in a vertical section, observing a kind of a feature of rising hotter mass. So that is exhibited whenever you talk about a plume. So when we talk about mantle plume, now mantle plume means heat which is produced in the mantle that starts to rise up in the formation or in the type of a plume. So this is observed typically in two portions of the mantle. So here, let's suppose you have the lithosphere. Beneath the lithosphere, we have the asthenosphere. This is the semi-molten portion, asthenosphere. And then underneath that, you have the Gutenberg discontinuity. This is the outer core. This is the region of mantle. This is your lithosphere. Now, significant amount of heat is produced from two portions. At one portion, that is in the asthenosphere, you have high amount of production of heat happening because of what? Because of radioactive substances which are found there. So you have high production of heat, due to presence of radioactive substances. Materials. And in the region of the outer core, you also have significant amount of heat which is present. Why? That is the residual heat, right? Here you will find residual heat. So mantle is getting heated up. Now this portion of mantle, let's say the asthenosphere. Now when the asthenosphere starts getting heated up significantly, let's suppose from a particular portion, that heat is being released, that heat is being discharged. Now this heat will melt the portion of lithosphere immediately above it, right? And it will melt the region immediately above it, will generate a rising column having a kind of a bulb-like head on top that will be rising. Because the molten materials are going to be lighter, because liquid is lighter than the solid, and because there is heat, they will start melting the materials above them. Similarly, in the case of the outer core as well. So at the region of Gutenberg discontinuity, let's suppose there is production of heat in this area. Now this will start melting the materials immediately above it. The materials will get molten, right? Molten materials are going to be lighter than the solids, and there is significant amount of heat provided. So this will melt the region around it as well. All around it, the materials will start getting molten, and these molten portions, they will start rising up, having a kind of a bulb-like feature on top, and it rises up. So that is what is referred to as a case of mantle plume. Now, earlier, it was thought that mantle plumes could be produced only from the region of outer core and mantle boundary. That was the perception, that only because of residual heat, mantle plume could be produced. But later on, it was found out that mantle plumes are also being produced from the region of asthenosphere. So both asthenosphere and the region of outer core, both of them can end up generating these mantle plumes. Now, what will be the impact? Let's say these molten materials are rising up. What are the impacts of this? So, impacts. Now, these rising columns of heat, they will heat up the layer above them. Now, mantle plumes can give rise to convection current in the mantle. Mantle plumes can give rise to convection currents in the mantle. Now, if there is a convection current on the mantle, what will be the impact on the ground surface? When we talk about the convection current on the mantle, what is the impact that we experience on the ground surface? We experience plate movement, right? You have upwelling in that particular region, the land can get pushed up, or there is a kind of a divergence, and a plate movement can modify the ground surface and also can end up initiate plate movement. How? They will bring about divergence in that region. Divergence. Then these convection currents, overall, they can bring about different impacts, but also this rising column of heat can give rise to prolonged volcanicity. Also, rising column of heat can keep on filling the magma chamber and give rise to prolonged volcanicity. Okay, so you have few areas across the planet where this is observed. For example, Reunion Islands in the South Indian Ocean, the Hawaiian Islands in the Pacific Ocean. There you have the presence of mantle plumes, which have been in existence for many million years, around 100 million years and more. There has been the presence of these mantle plumes in these particular area. So basically, this is the recreation of what appears to be a mantle plume. So observe here at the region of the Gutenberg, that is where primarily that heat is produced, the residual heat. It will have a kind of a bulb-like head on top, and it will continue to rise up. It can lead to various features: upliftment of the landmass in a certain area, volcanic eruption in a certain area, development of cracks in a certain area, movement of the plates with respect to each other. All of that can be initiated by these mantle plumes. So, mantle plume is the convection of magma in narrow columns in upward direction from the core mantle boundary, forming a mushroom shaped core to the plume, cap to the plume. Mantle plume magma is hotter than the surrounding magma because it is provided consistently with that heat, which has given rise to that plume. So that is why it rises. Now, position of mantle plume is fixed. It is not as if the mantle plume is present here and tomorrow it will shift somewhere else. But it is not something which is going to be continuous across the history of the planet of the Earth. It might happen that over 150 or 200 million years, a mantle plume is in existence in one particular region, and let's say after 200 million years, mantle plume has emerged in certain other area. Now, mantle plumes plumes can also sometimes be created due to what? They can be created due to excessive heating of asthenosphere. Heat present in the asthenosphere. So from there also, mantle plumes can be produced as a process. Okay. Now, these mantle plumes, we get an ideal understanding of these mantle plumes with the help of what we observe on the ground surface as volcanic hotspots. Volcanic hotspots generally they tend to lie above the region of the mantle plume. Now, magma chamber we are aware generally lies at the boundary between lithosphere and asthenosphere. Now, this magma chamber is continuously supplied with molten materials through the presence of that mantle plume, and that ends up creating a kind of a volcanic hotspot. So what is a hotspot? Again, an English terminology. You hear about biodiversity hotspot, you hear about a kind of, let's say, a crime hotspot, accident hotspot, etc. So what is a hotspot? So when we say, or when we talk about a hotspot, it is that region where frequency of an event is very increased, where a particular event happens quite frequently, quite significantly. So when we say a hotspot in terms of volcanic hotspot, these are those areas which end up experiencing and exhibiting continued volcanism for many, many years, millions of years altogether. In certain cases, more than 100 millions and so more. So that is where you have these volcanic hotspots. Now, these volcanic hotspots, they are able to continue that volcanism because the magma chamber is continuously filled up by the molten materials. And why and how is the magma chamber filled up? With the help of mantle plume. So, a hotspot is a volcanic area on Earth that exists over a mantle plume. This mantle plume fills up the magma chamber. Okay, they will fill up the magma chamber. Now, these hotspots also end up creating a chain of volcanic landforms across the land. And by taking a look at the chain of these volcanic landforms, you can also get an idea about since when this eruption has been happening, what are the types of eruption that has been happening, and so on. And also, what is the direction of plate movement? That is also something which can be deducted from this or deduced from this. How? So these hotspots, here you have to understand that the magma chamber is present in the lower region of lithosphere, in the portion of asthenosphere lithosphere boundary in many of the cases. Now, that magma chamber is fixed, but the plates above them, they continue to move, right? The plates above them, they exhibit a kind of a continued motion. So as the plates above them, they continue to move, the volcanism carries on, creating a chain of landforms. How? Let us see. So suppose this is the landmass, and here you have the magma chamber, a very large magma chamber created by the molten materials which have been brought by the mantle plume. So you have a very large magma chamber. Now, in this case, when you have the eruption which happens, that will lead to a volcanic landform, let's say here. A volcanic landform will be created. Now, let's say this eruption has happened over a span of 500 years, 1000 years. But the plates, they end up moving. The plates are not fixed, the plates are moving continuously. So if we say that this is a kind of a plate, let's suppose it is moving in this direction, so the volcanic landform will also be carried on top of it. So after some time, you will observe that this volcanic landform, because of the plate movement, it has shifted somewhere here. Sometimes it also happens that despite that shift, it still, for a temporary duration, retains its connectivity to the main magma chamber. Sometimes that also happens. So continued volcanism will be observed even in this area, despite the fact that it has shifted. But then the newer eruptions will happen in which region? Newer eruptions will happen in this particular area. So a new landform will be created. Now, the plates are consistently moving. So after some time, again you will come across a scenario where all of these plates would have moved. All of these landforms would have moved. The earliest one would have come somewhere here, then the other one would have come somewhere here. Meanwhile, a newer one would have been created, would have been formed here, and then a new eruption would be happening here. So this is where the oldest eruption would have happened. This is for the oldest eruption. Right? And this is where you have the newest eruption. So by this, you can gain an idea about the plate movement as well. That what is the direction of movement that the plates are indicating. Right? So again, I would repeat. So in this case, in this image, if you observe, look at this. This is the magma chamber here. This is the magma chamber. Then here, basically, look at it. Here also you have a volcanic landform created. Here also you have a volcanic landform created. Here also there's a volcanic landform created. But the tectonic plates, they are moving like this. So imagine at one point of time, this particular landform that you see, it would have lied immediately above the region of the magma chamber. But the plates are consistently moving. That is how they get created, and you have a chain of landforms created. Another example, if you observe the mantle plume in the region of Hawaii. So here, observe, this is where you have the Hawaii, the present location of Hawaii. Now here you have the magma chamber. This is your magma chamber, continuously supplied by molten magma with the help of the mantle plume, magma chamber. Now, you will observe that the oldest of the volcanoes, so here the oldest of the volcanoes here, that is the Suiko ranges and the Suiko volcanic eruptions, all of these also, all these volcanic lands, they have been created as a result of the same volcanic eruption which happened at Hawaii. That means at one point of time, this particular region that you see, this would have also lied here. That means at one point of time, the plate would have moved like this and then would have moved like this. That is how you have the chain. So observe here, oldest volcano, which is far away from Hawaii, this has erupted around 5.1 million years back. This has erupted 2.6 million years back, 1.8 million years back, 1.3, 0.8 million years back. And then you have the present day eruption, what we refer to as the Hawaiian Islands. So two very prominent and major hotspots are the Reunion Islands in Indian Ocean. Locate these Reunion Islands in the case of Indian Ocean. And then you have Hawaiian Islands in the case of Pacific Ocean. You also have the Aleutian Islands, but that is not as major as these two. Pacific Ocean. These are your hotspots. Both of these are getting supplied by the mantle plume, leading to frequent eruptions. Okay, is that understood? Shabir, from where from come magma? Magma comes from the region of the mantle. What is magma? Magma is molten material in the interior. So that is provided with the help of the mantle plume. Shalu, convection is moving, but plume is fixed. Convectional is moving, but plume is fixed. Yes, fair enough. So understand, this is not interrelated that if there is a convection, so if always we have talked about the same fact, let's suppose this is the region of the crust, this is the region of the mantle. If there is a convection current here, right, this convection current can stay in the same region. The plates can end up moving invariably, right? So that is why when you come across this particular point that the position of the mantle plume is considered to be fixed, that is why I have clarified, not throughout the history of the planet. It is fixed in a temporary duration. Let's say for 500 million years, the mantle plume will be in that region only. It might absolutely be possible that, let's say, 500 or 1 billion years later, mantle plume shifts somewhere else. Okay, I hope that is understood. Kishan, in caldera, where they subsidized, subsidization is economy, subsidence is geography. So where they subsided, because beneath these cracks there has also solidified rock, and if the chamber is vacant, then whole solidified lava should collapse. That is why when the weaker portions develop, only those will collapse, right? It is not as if the entire mountain will start crumbling, sinking, and will disappear. Sometimes even that also happens. For example, take the open up Google Map today, look at Crete in Greece, look at the region of Tonga in South Pacific. They will hardly give you an expression or an impression that there has been a kind of a volcanic eruption there, because significant portion of that has collapsed. Okay. How many landmarks can be obtained by mantle plume? Landmarks in the sense mantle plumes can lead to significant amount of volcanic hotspot. They can leave a trail. Reunion Island volcanic hotspot that you have, that Reunion Island volcanic hotspot has been responsible for formation of the Deccan Plateau in India. So imagine Deccan Plateau and then chain of mount islands in the region of Indian Ocean. They have been created from the same hotspot. Okay. Is in Reunion Island the hotspot is present? Yes, it is present. Difference between magma chamber and a hotspot. Magma chamber is anywhere where you have a molten material which is present. It can get extinguished within a moment of time. Let's say within 50 years, 100 years, 200 years, that magma chamber can become dormant, can become extinct. In the case of a hotspot, hotspot is a place where that eruption will continue to happen. Hotspot will also have a magma chamber. The difference is that in the case of hotspot, the magma chamber is continuously filled up because there is a mantle plume. Okay, and what is the difference between convectional current? It is not conventional current, it is convectional current and mantle plume. Mantle plume is basically the heat which is produced that rises up. Now, that heat which is produced can give rise to a convection current in existence. Convection current can be produced in many areas. Not all of them are going to be categorized under mantle plumes. Mantle plumes, when you have a significant rising column of molten materials which is happening in a region, it can give rise to a convection current. Okay? And that means mantle plumes are also evidences of plate tectonics. They give rise to plate tectonics, yes. Subsidence of Joshimat, I had told you in the initial classes itself that kindly take a look at a detailed video that we have done. It is available on YouTube. It is a YouTube shorts, in fact. You will get multiple reasons why that subsidence is happening. In case of caldera, it will further erupt in future. Chances are negligible because the magma chamber is consumed. But sometimes it can also happen that a further recharge of magma chamber can happen due to subsidence or due to convergence of the uh, land mass or convergence, oceanic convergence that can also refill magma chamber. That can also happen. Okay. Sadhana, magma chamber is located in the lithospheric asthenosphere boundary. Hotspots will never have an empty magma chamber. Yes, correct. Right. And this is the best thing that I have received till now. Everything that you are teaching us, make it in a point format. I am not making notes. It will help a lot. Okay. So if I will make your notes, and that is never going to help you. I'm trying to be as polite as I can. It is never going to help you out. See, please understand, try to make notes on your own as well, regardless of how less a time that you have. UPSC's examination is not a shortcut, my dear friend. It is not as if I'll get two small chits from here, four small chits from here, and I will. It is not your graduation exam. It is not your class 10th or 12th exam. This is the civil services examination. The brightest of the minds of the country are going to appear for the examination. And please don't try to find a kind of a shortcut in this. I have already given you a summarization of the previous topics. And again, I had told you this is never going to help you. Unless and until you do it on your own, it is never going to help you. So, despite the fact that I might disappoint you beyond your wildest of the expectation, I will take the risk of disappointing you in this because it is never going to help you if you rely on the. Now, if I will make your notes after a point of time, the next demand, which I have already received by many candidates, that show us by writing an answer that how an answer is written in the class. So answer writing should also be done. So eventually do one thing, give me the UPSC form also. I will write my name there, I will fill up the form, and in your place I will appear for the exam also. So please understand the examination that you are appearing for. For a moment, take a pause and appreciate the gravity of that examination. Right? The government is trying to make you a civil servant, a bureaucrat, a chief secretary, maybe someday. And that is where you require a lot of hard work, my dear friend. Okay. Not exactly like a solar flare, but the movement of mantle plume can be thought about as a solar flare. And if magma outcome from Earth, how make Hawaii other islands? Hmm. Because the magma in that point of time is being resupplied. Always understand, magma chamber in the case of a hotspot is continuously being resupplied by the molten materials with the help of the mantle plume. That is where you will have the condition of a continuous supply of the mantle plume that will keep on filling the magma chamber, right? And that is where it will continue to indicate volcanism for millions of years as long as the magma chamber gets refilled. Okay, right? Yes, Shalu, that is correct. Mantle plumes can give rise to convection current. Does not mean everywhere there is a convection current, there is a mantle plume. Sometimes convection currents can be given or can come into existence even from the region of asthenosphere. Many of the times that will not be regarded as a mantle plume. Okay, is that understood? Last question I'll take. In the first class, you said that 1 to 5 lectures are of geomorphology, but this is the sixth lecture. Yeah, I understand. What do we do now? So we are crossing the time. So that 1 to 5 lectures is of geomorphology. The modules are of geomorphology. Now, if we take, let's say, one module to understand, one lecture to understand earthquake, one lecture to understand volcanoes. How can you expect that the entire geomorphology? But don't worry about it. Please understand, I will never leave you high handed in the sense that the syllabus is not completed. This is where, regardless of whatever come may, the syllabus will be completed. These are the portions of concept building. Next comes climatology, which is heavier on concept. This is still lighter on concept. Climatology is much heavier on concept. Once you get used to the conceptual portions, the later portions, mineral distribution, etc., that is something which can be covered in a jiffy. But this conceptual portion, once you understand that, that is the physical geography, world would be understood, the Indian portion would be understood, and significant other connotations would also be understood. So have patience, just understand what is being done on a daily basis. Just do your job, we will do our job, don't worry about it. Okay, now here basically we come to the intrusive volcanic landforms. Now, intrusive means something which is present on the inside, something which is present on the interior. Now, intrusive volcanic landform, so this basically ends up happening when the molten materials, they are unable to break through the surface. Sometimes that can happen. It can happen, let's suppose, and even in India we have experienced that. Let's suppose on top of the crust, or the crustal layer forms a very thick, more than 5 to 10 or even 20-kilometer thick of hard igneous rocks. So the molten materials won't be able to come out. So that is where you have the molten materials losing their heat to the surrounding region, the magma chamber losing its heat to the surrounding region, and cooling down in the process. Sometimes it can also happen. Let's suppose this is the ground surface. This is where you have the magma chamber, right? So molten materials, they try to come out. But in between, let's say, they spread out in between the layers of the rocks. They spread out between the layers of the rocks, molten materials. And they will solidify, let's suppose. So this also solidifies. Here also, let's suppose it has spread between the layer of the rock, it has solidified. Here also, let's suppose it has spread between a layer of rock, it has solidified. Even this magma chamber has lost its heat, lost its energy, and solidified. Now here, it will form what is referred to as intrusive igneous rock. We had studied that igneous rock is of two basic types: extrusive, formed by the cooling of lava; intrusive, formed by the cooling of magma itself. So you have extrusive and intrusive igneous rocks. Now, when you have the extrusive and intrusive igneous rocks, these are the intrusive ones. Igneous rocks. Okay, you have the intrusive igneous rocks. Now, over a period of time, this top portion, let's say, this gets eroded, this gets removed. This top portion gets eroded and removed and weathered by. So, as the top portion gets removed, these bottom intrusive rocks, they are exposed to the surface. And that is what is referred to as intrusive volcanic landform. Now, these are basically of various different types. The intrusive volcanic landforms are of various different types. You have batholiths, you have lopoliths, you have phacoliths, you have sills, dikes, laccoliths. All of these are the types of these landforms. Now, these have been classified purely on one basis. That is the shape in which they have solidified. the manner in which they have been solidified. So this classification is done on the basis of the shape in which they have solidified. Okay, the shape or the characteristic in which they have solidified. So for example, when we talk about it, we'll talk about the shapes of it, the formation of it, just a brief about it. So here, the cooling may take place either on arriving the molten materials, either after arriving on the surface, or the cooling might also happen in the interior itself. Now, according to the location of cooling of lava, igneous rocks are categorized into plutonic, that is the intrusive, and volcanic rocks. That is something we have seen in the classification and categorization of rocks itself. Now, here we have various different areas in which they get cooled. So, for example, take a moment's look at this image. In this image, you will come across the fact here. Let's suppose if you consider this entire area, this entire base appears to be an ancient magma chamber. And observe how from various different areas the magma has tried to come out. Magma has tried to come out, but has solidified in the process. It has solidified in the process. So depending upon the shape in which they have solidified, observe here, the shape of solidification of magma is a kind of a dome shape on top and flat base. Here, if you observe the solidification of magma, it is a kind of a horizontal solidification. If you observe the solidification here, the entire portion of the magma chamber, that in itself ends up getting solidified. Right. So that is where the solidification happens. So the entire classification of the intrusive landform is purely dependent upon how and where that solidification is going to happen. So let us take a look at them. So we start with the aspect of batholiths. So when we talk about batholiths, they are created when the entirety of the magma chamber in itself loses heat and slowly solidifies or cools down in the portion of the magma chamber, wherever the magma chamber was present. Later on, because of various different endogenic forces and forces acting from interior, many of the times it is uplifted and the upper portions are degraded as well. That is when it is exposed to the outside environment. Observe this. The entire dome-shaped formation in this entire region, this is a batholith. So imagine that at one point of time, this would have been a magma chamber. So imagine that above it, you would have had many different land masses and crustal portions which have been weathered, which have been eroded, the lands have been pushed up, pulled down, every geomorphic processes have happened, and now this stands exposed. So batholiths are cooled portion of the magma chamber. The entire magma chamber in itself cools down. It is exposed on the surface only after denudation process. So denudation processes both when the top surface is eroded or the top surface is broken down due to weathering. Okay. Then we have laccoliths. Here, observe this. A dome-shaped portion. Now, this is also an intrusive landform. Now, here also, molten materials would have tried to come up, but the crustal portion would have been so hard that they would have not been able to break through. So that is where they would have been solidified where they are. That is the laccolith. Now, laccolith Just like in the case of every intrusive landform, will have a connect to the ancient magma chamber that also would have completely solidified. No molten materials, by the way, never molten materials will be found anywhere near these intrusive landforms, because there has been a long time which has basically elapsed since their solidification. Because the topmost portion, imagine on top of it, you would have had a crustal layer at one point of time. All of this has been eroded significantly, and now this stands exposed. So here it will have a flat base, a dome-like feature on top, and maybe a channel, a solidified channel, which would have connected it to the ancient magma chamber. So the magma chamber in itself, when it solidifies, batholith. When the magma tries to come out, solidifies in a dome-like portion, you have a laccolith. Then we have a lopolith. Lopolith is where you have a flat top and a shallow convex base. So here, what is it? That the shape will be a flat top and a kind of a very shallow convex base. So maybe the magma would have tried to come out from the ancient magma chamber. Let's suppose the ancient magma would have tried to come out, but would have solidified in this shape and in this process. So that is where a lopolith is created. So that is how you have the creation of these intrusive landforms. Now, how do you study this? When you have to study something, you need to develop a kind of an approach, whether I'm studying for what kind of question. So in this, the type of question that can be expected is a one-liner match the following type, right? A one-liner match the following type. For example, if I give you a question that batholith on one side, lopolith, laccolith, right? Here I tell you solidified magma chamber. Here I tell you dome shaped or connected to magma chamber, right? And here I tell you flat top with convex base. So when you have these kind of questions, you will be asked to match the following. So batholith is which one? Batholith is solidified magma chamber. Lopolith is correctly matched. Laccolith is A. So that kind of match the following kind of a question can always be expected from this particular area. Okay. So accordingly, you can just take a look at it in a very brief manner, purely for your prelims perspective. Then we have facholiths. Now, facholiths, when we talk about facholiths, let's say, now facholiths are basically when everything is cooled down, right? When the materials are cooled down in between the layers of the rocks. Let's suppose the rocky layers, in general, when the rocks and the layers of the rocks are present, in general, the layers of the rocks, let's suppose, they are present like this. Now, there's a layered format. Now, let's suppose there's a compression of the rock which has happened. So this entire rocky region will get converted into a kind of a fold of sorts. So this entire rocky region will get converted into a kind of a fold format. Right. It will get converted into like a fold format. So here, if the molten materials, they start to come out, and the molten materials, they start to solidify in this region. in this region, right, along these folds. So that is basically what is referred to as facolith. So that is what we have as a facolith. So basically, it is a wavy mass of intrusive rocks found at the base of synclines or the top of anticlines. So whenever the rocks they get folded, so whenever the rocks they are folded, they will develop a feature like this. This is what is referred to as the upfold is what is referred to as anticline, and the downfold is what is referred to as syncline. Right. So when they get solidified at the region of anticline or syncline, that is what we have as facolith. Then you have sills. Sills and sheets. They get created when the molten materials they spread out in horizontal layer between the rocks, and there they get solidified. If that spread out is very thick, we refer to them as sills. If that spread out is very thin, we refer to them as sheets. But they are horizontal spread outs, which happen over a very large distance. So that is basically sills. Okay. So this is how a typical sill will appear to look like. When you take a look at a sill, so here, observe this in the mountain. A kind of a horizontal layering of sorts. That is what is referred to as this will be a sill. So basically, when the molten materials they spread out in horizontal layers and then they solidify, that is what is a sill in general. Okay. So many of the times in between the layering of the rocks, you have various different types of rocks. That is where it will start spreading out. Sometimes it also spreads out in very thin layers. So thin layer, it is called sheet, and thick deposit, that is referred to as sills. Okay. Then after that, we have also the case where sometimes the molten material tries to come out in vertical section, loses heat, loses pressure, and solidifies in vertical wall-like formation itself. Those are what are referred to as dikes. So when they solidify in a vertical wall-like formation, those are what are referred to as dikes. Okay, so that is what we have as dikes. These are also sills, and dikes are very rich source of mineral availability. Okay, lopolith are also horizontal, so they even lacolith is horizontal, but the shape is different. Lopolith top is flat, the bottom is not flat, the bottom is having a convex shape, right? Whereas in the case of lacolith, you have the bottom is flat, the top is dome. So the shape is different. In the case of sill, it is absolutely horizontal in that case. Now, we come to the type of eruption depending upon the type of magma and the type of or the chemical um, component of magma which is present. So that contributes to or controls the eruption style. So when we talk about the type of magma, you can have two types. One which is very fluidic, easily flowing, other which is very viscous, which is not going to flow very easily. So they are classified as mafic and felsic. Mafic basically means rich in magnesium and iron. Rich in magnesium and iron. And when we say felsic, very rich in silica. Rich in silica. Consists of feldspar and quartz in general. Now, mafic will have higher density. High density, flows easily. Now here, this has got silica. So forms large silica crystals. Large silicate crystals. And when we have large silicate crystals, that means difficulty in flow. That means it is viscous. Okay? It doesn't flow easily. So if it doesn't flow easily, it allows for the penetration of air bubbles in between as it tries to move from one region to another. So that is why the air bubbles, they keep on penetrating these molten materials, and that is where the density is lower. Density is very low. In the case of mafic, you don't have any silicate crystals which are created. So the flow is quite easy. The flow is quite significantly sufficient. It flows almost like fluidic water that you observe. Then after that, here you will observe another aspect. This is going to be darker in appearance. In appearance, this is going to be light colored. In appearance. Okay. So that is basically the kind of magma. So something which flows easily. Does it require explosive eruption to come out? Obviously not. When something which flows very easily will allow very easy escape of gases as well. So it does not require an explosive eruption to come out. Generally, you will observe that the mafic magma is many hundred degrees Celsius warmer and hotter than the felsic. So this is significantly hotter. Very high temperature. Now, because it is able to flow easily, it is able to flow like water, there won't be enough amount of difficulty for the materials to come out of the surface. If there is a volcanic vent, these materials will start seeping out and spreading across the entirety of the region. So this will be generally associated with non-explosive eruption. And there's another factor why you will have non-explosive eruption in this case. Here, when we say a mafic magma, now mafic magma, again, high temperature, flowing easily. All the gases will be easily escaping from that molten material. Now, if the gases are escaping, obviously, those gases will not induce very high pressure while they are coming out. So that is where non-explosive. In the case of felsic, it doesn't flow easily. It forms large blobs or chunks of molten material, which have trapped a lot of air. So for this material to come out, the entire blob will be forced out at once. And for that, you require a high pressure. So generally, felsic magma is associated with significant amount of trapped air, and that is associated with very explosive eruption. Large air is trapped of air is trapped, leading to explosive eruptions. So the type of eruption which occurs, the type of eruption which is observed, that is very much dependent upon the type of magma that you have. Here, why is it that felsic, again I will repeat, why is it that felsic is not able to flow easily? Because you have formation of very large silicate crystals and they inhibit the flow. So that is where, in a case where something or molten material is not flowing easily, it will stay there slowly and steadily, it will build up, it will crumble, roll down. In that process, lot of air will also be induced. So that is why it has got lesser density. Similarly, while the felsic magma is still in the portion of the magma chamber, there also it will start forming large, think about it, boiling bubbles, right? Blobs. And they will have a lot of air impregnated. So, if in a very simplistic diagram, even though that is not the correct depiction, in a very simplistic diagram, let's suppose this is a volcanic vent, this is a volcanic landform, and this is a magma chamber. Now, from this vent, if suppose such large materials or blobs, they try to come out at one go because they have trapped a lot of air in between, they will have to cause this kind of an explosion, right? Because they will require enough amount of pressure to come up, to be pushed up. So always that pressure will bring about an associated explosion. On the other hand, if let's say you have very fluidic lava or fluidic magma, now that fluidic magma, if there is a weak point, if there is a crack, it will automatically come up, it will start pouring out. So that is where the explosivity, the non-explosivity, that is very much determined by the magma. And mafic magma is much hotter, much hotter. So that is where you have all of the things completely in a very molten state, in a completely fluidic state. So mafic magma, rich in magnesium and iron, darker in color, viscosity is low, means it will be able to flow easily, and the gas content is also low. So the eruption style is non-explosive. You have a non-explosive eruption. When we talk about felsic magma, here the silica content is very high. So here the viscosity is high because silicate crystals are formed and they are unable to flow easily. So that is where, if the material is unable to flow, it requires a high pressure to break through the surface, and we have an explosive eruption. Okay, so in a way, the amount of silica which is present in the magma, that becomes a determining factor in terms of the fluidity, in terms of the flow, in terms of the type of eruption. So quantity of silica, amount of silica becomes the determining factor for flow. Okay, so that is the aspect of the eruption style. Now this is relevant for your prelims examination. This is relevant for your prelims examination. So use this chart for your prelims examination. Okay, that what kind of flow is associated or initiated depending upon the type of magma that we have. After this, we come to the global distribution of volcanoes. Yes, Pinto, correct. Now we come to the global distribution of volcanoes. Where is it that across the globe you come across volcanic eruption? So volcanic eruption, now if you have to take a guess that where volcanic eruptions they do occur, so now you will be able to make a much informed guess. So you have plate boundaries, plate boundaries, then you have, and here also you have to be very pinpointed in which plate boundaries. So wherever you have oceanic convergence, right? let's suppose wherever you have oceanic convergence, divergence, these are the major areas. Divergence, sometimes in rare cases along a crack, but in global distribution, that is not something which is very important. Then after that, hotspots, wherever we have volcanic hotspots. So if we take a look at this map, this is like a poor version of the map. So here, observe all around the region of the Pacific Ring of Fire is dominated by volcanic eruption. Now here, observe certain areas. For example, this is where you have the Tonga eruption. This is where we had the Tonga eruption. Okay. Now, Tonga eruption, one of the most massive eruption since 1991. 1991 was another year where you had a very massive eruption, also regarded as one of the most explosive eruption in this entire century. That was the Pinatubo eruption. The Pinatubo eruption in this region. Then in the 1800s, the most massive and the most explosive eruption which occurred was the Krakatau eruption. Krakatau eruption. So all around now here, why is it that Krakatau erupted? The oceanic portion of the Indian land or Indian plate that is undergoing subduction. That is why Krakatau eruption happened. When Krakatau eruption happened, it was estimated that, or what is now recounted, is in that region immediately, the sunlight was completely blocked for many weeks. And the explosion, the impact of the explosion could be felt as far as away as Turkey and as far away as Japan. So that was the amount or the explosive coefficient of this eruption. Now, when Tonga eruption happened last year, now during that Tonga eruption, the shock waves created by that Tonga eruption, they were so massive and they were so powerful. They traveled the entire planet twice. Indian Meteorological Department has got a weather station at Goa. Now that observed the change in atmospheric pressure which happened because there was a Tonga eruption in South Pacific. Now this eruption was so significantly powerful that it has created a caldera in that region. So if I take you to a more modern map, a better looking map in general. So when you have to write an answer for this, so first of all, you have to write why these eruptions happen, then the zones where these eruptions are very common. So what are those zones? You have the Circum-Pacific Ring, Pacific Ring, the other zone, Mediterranean, then after that, Mid-Atlantic Ridge. It is this Mid-Atlantic Ridge eruption which has created the island of Iceland, right? So Mid-Atlantic Ridge. Okay. So all these are the major points. Now here you can also talk about this region as the Indonesian Arc. Indonesian Arc. Barren islands that you find in Andaman Nicobar, those barren islands are the topmost eruption or the northernmost eruption of the Indonesian arc that is created as the oceanic crust of the Indian plate is subducting underneath. So all these you can always bring into the picture and always keep an eye out for current affairs. Any area where the eruption is happening, ideally what you should do is look at the location of it. For example, La Palma eruption, which happened in 2021, that was significantly in news. Now, La Palma is where? This is your La Palma eruption, very close to the mid-Atlantic ridge, but also across a fault line which has developed, a kind of a transform fault line which has developed in that region. So that is where La Palma eruption came into picture. So slowly and steadily, when you are persistent with the news headlines, you won't be needing to learn this volcanic names from a particular book. So automatically, you will be able to recall much more than what I am trying to tell you right now. So this will be a natural progression. Don't hurry into it. It will come provided you are very regular in the portion of current affairs. Now we come to the portion of folding and faulting. So whenever a landmass, let's say, gets compressed, gets expanded, gets pulled or pushed, the landmass consisting of various different rocks, they will end up behaving in a certain manner. They can develop a kind of a large crack. They can develop a kind of a fold. So that is what we will study in the portion of folding and faulting. So folding and faulting can help us understand the existence, the formation of many different types of landforms around us. Himalayas, a result of folding. Vindhyas, a result of faulting. Western Ghats, a result of faulting. Tibetan Plateau, a result of faulting. So many different landforms around us we can understand easily if we get an idea about whether folding or faulting is happening. And this is basically driven by compressional and tensional forces. Compressional and tensional forces. Okay, now let us understand that. Now suppose, first of all, we'll take a look at folding. Now suppose this is the landmass. Now this landmass is getting compressed from both ends. Observe the fold. As long as the force that I am applying from both ends, that is equivalent, that is similar, the fold will be very much symmetrical in nature. That is, both the ends of the fold will indicate a similar angle. But over a period of time, let's suppose this is the Eurasian landmass, let's suppose this is the Indian landmass, they are applying compression. Indian landmass is moving at a significant rate. Observe the fold. The fold is getting tilted. Eventually, observe what happens. Fold becomes almost horizontal. So folds are also classified based upon and dependent upon how that folding is happening, why that folding is happening, and how much difference of force is being applied from both the ends. So for example, a bend in the rock that is a response to the compressional force, that is referred to as the compressional force. Now, compressional stress will give rise to anticline and syncline, anticline and syncline, right? Now, that is anticline and syncline is the up thrown and the down thrown part. Now you have various different types of fold. Different types of fold depending upon what is the shape of the fold. Fold can be in the very initial stages when the land masses have just began to apply the compressional forces. In the initial stages, the fold will be somewhat like this. But let's suppose the forces increase from one end, the folding will also end up varying. So here you will observe in the type of folds you have symmetrical, asymmetrical, then recumbent, and then you have nappy. You have other kinds of folds as well, not very important. These are the major ones. Now all of these end up varying or getting distinguished and differentiated from one another purely based upon the magnitude of forces being applied at different ends. So for example, here, let us take the case of symmetrical fold. In the case of symmetrical fold, you have equal forces which are being applied from both the ends, right? Equal forces which are being applied from both the ends. So if you observe here, See, on the ground surface, it appears absolutely normal. If you are an individual Tom, Dick, or Harry walking on the ground surface, you will barely be able to recognize that there is folding happening underneath because that fold has been eroded. So observe this fold. Observe this kind of a fold. This is symmetrical. This will only happen when the folding has just begun, when the forces are very equal on both the ends. So in the region of the Andes ranges, you will find these kinds of folds where the forces are equal on both the ends. So same forces, equal forces from both ends. Okay. Then when we talk about asymmetrical fold, observe this. Now, an individual person who is walking or here, that individual person will not even get to know what kind of a fold it is. But observe the rocks. Observe the fold in the rocks if you can. You will observe a kind of an asymmetry. Right? So that means from one end, the amount of force has increased. From the other end, the amount of force is not equivalent. So from one end, if the amount of force has increased, observe that the fold starts getting irregular or asymmetrical. If the force keeps on getting applied, the fold will become almost horizontal. Does not mean that the mountain will become horizontal. The rocks, the folds will become horizontal. Because regardless of the asymmetry, observe that from above, the mountain will give you the shape that you generally associate the mountains with. It is the rocks underneath which are undergoing that folding. So in the region of Alps, in the region of Himalayas, in fact, in the region of Himalayas, as you move from Shivaliks to the Great Himalayas, you will observe a variety of different types of folds because the Great Himalayas, they have been getting folded for around 60 million years and more. The Shivaliks have been experiencing folding very recently. That is only around 10 to 15 million years back. So that is where in the Great Himalayas, you will find many different kind of deformed folds, whereas in Shivaliks, mostly to the category of symmetrical or asymmetrical. Then we come to the horizontal fold or recumbent fold, which is also referred to as a sleeping fold because of its deformity. So here, when you talk about it, yes, my dear friend, in geography, million years is something which is very recent. Cordilleras basically are the ranges of mountains parallel to each other. They are referred to as cordilleras sometimes. So, what happens? Let's suppose you have a mountainous area. Now, in this mountainous area, the rocks are getting compressed. In this region, the rocks are getting compressed due to the fall, due to the compression. Now, eventually, if the rocks develop a bend like this, if the rocks develop a bend like this due to compressive force, so what is going to happen? This is a sleeping fold. This is a horizontal fold. Observe this. This is a kind of a horizontal fold. So that is what is referred to as recumbent fold. Now, if this pressure keeps on getting increased, what will be the consequence of it? If this pressure keeps on getting increased, at this point of deformation, it will reach an elastic limit. It cannot get folded anymore. So it will crack, it will break. So now the upfolded portion is no longer going to be in contact with the base. So now the upfolded portion, they are free to, in a way, move. So that is where many of the times you will find that this kind of a fold is also created where it has been broken. This is what is referred to as a broken fold. Broken fold, or what is referred to as a nappy fold. Example. Now, recumbent fold you will be able to find in the Himalayas itself. So, example, Himalayas. And broken fold also you'll find in Himalayas. In many regions of the Great Himalayas, the folds have been created where the broken portion has moved few kilometers from the region of breakage. So observe this. On top of it, the mountain appears absolutely normal as it is. Observe the folds. So here you have the folds of the rocks. Observe this area. So this at one point of time would have been connected, but the rocks could not get deformed anymore. The rocks could not get compressed anymore. So this is what is a broken fold. This is what is referred to as a broken fold. So when we have a broken fold, in that case, the compressional stress that surpasses the ductile characteristic, the deforming characteristics of the rocks, that is what we have as the condition of broken fold. Lappies are different. Lappies are something very different. Where do you find the broken folds example? Himalayas again. Yes, Alps also you'll find the case of nappy, both in Himalayas and Alps. Okay. Now, faulting. Faulting is a development of a crack on the rock that can happen due to various factors. It can happen because of compressional stress. It can happen due to tensional stress. For example, here, take this material. If I compress this, it will get folded. Now, if I compress this pen that I have in my hand, do you think it will get folded? Or do you think it will get broken? It will get broken. It will develop a crack. It will break. So that development of a crack can be regarded as a fault. So when we talk about fault, you have various different types of cracks. Not every crack is referred to as a fault. So that is why look at this particular portion carefully. So here, a sudden stress on the rocks may reach the rupture point, resulting in cracking and breaking of the rocks. If there is a breaking of a rock without any relative movement, so let's say if the rock has broken and there's a development of a crack, but this portion and this portion, they are as it is, they are not moving with respect to each other, then this is referred to as a joint. That is referred to as a joint. Now let's suppose there is a development of a crack and there is a portion which is moving with respect to each other. Then this is referred to as, if there is a relative movement, then it is referred to as a fault. Now this motion is going to happen across this entirety of the area. Let's suppose this is the rock surface. So this motion will be happening across this entirety of the plane region. So where the motion is happening, that is referred to as a fault plane. Okay. So this fault develops due to both compressional and tensional stresses. Let us take a look at it, a quick glance at it, that how that pans out. So a normal fault, very normal fault created due to tension, tensional force, pulling force. Let us understand this. Suppose we have a rock. Rocky layer. Now there is a tensional force. it will get thinned out ever so slightly. If I try to pull it, even though neither do I have the enough physical power, nor do I have the financial capacity to break it. Let's suppose I become very brave, I try pulling it up, it will thin out in between. But then what will happen? It will develop a kind of a crack. A crack will be developed here. A crack will be developed maybe here also. A consistency of this pulling force will deepen the crack. Right? So the crack has basically formed a joint. Now, if the tensional force still exists, what do you think will happen? Here, this portion starts to slide down, isn't it? This portion will start to slide down along these regions of the cracks. It will start to slide down now. So now what condition that you have? You have a land surface which appears like this. A portion has simply slided down. So that is why many of the times, even while traveling from where you live to any other place that you have traveled, you would have come across many landforms which would have indicated a plain region, and suddenly there is not a mountain or a hill, but there is a rise which is there, right? An upland area that you can take a look at. You can basically, even in certain cases, have a run at it. You can run and climb it, but there's a kind of an upland of sorts which is created. That is what is caused by a normal fault. And this formation, which is done now, that is what is referred to as an escarpment. For example, in the region of Western Ghats, Western Ghats are not referred to as mountains. Western Ghats are not referred to as hills. In some local areas, they are referred to as hills. But these Western Ghats are an ideal example of escarpments. Okay, we'll talk more about it when we come to Indian geography, that how this escarpment was created. And the portion, very interestingly, that I want you to open up the map of India after today's class. Look at the portion to the west of Western Ghats, where, look underwater. You will find a bright blue area, means a shallow region. So the portion which was separated, the portion which slid down, that portion presently is underneath the region of Arabian Sea. So that is also a reason for many other geophysical characteristics across the western coast of India. This is the reason why Western Ghats, they have almost steep wall-like slope. That is because of the creation of an escarpment. You have the tensional forces which are created as a result of this. Okay, a tensional forces create this. Now we come to reverse fault, the opposite of it. So it is a result of compression, compressive forces. So let's say if I compress this, it might not get folded, it might break. So if I have, let's say, a rock. Now, if I'm providing compression here, it will develop a kind of a crack eventually. Let's say development of a crack happens. This crack eventually deepens, right? Now, if I am going to compress it furthermore, what do you think will happen? Will it slide down as was the case with the normal fault? No. This time, a portion will be pushed up. A portion will if these are the two ones, one will simply climb over the other. So as a result of that, this upward movement appears to be opposite to what gravity would do, reverse of what gravity would do. That is why reverse fault, because it creates an upward movement of the landmass. So the landmass which gets created will have an upward movement like this. This landmass has been pushed up. Right? Why? Because of compressional force. This is the exact formation of the Tibetan highlands. This is the reason why Tibetan highlands on an average are 5 kilometers higher. There is much more complicated geophysical characteristic involved as well, spreading out of the landmass, weakening of the crust as it rises up beyond a particular height, saturation of height, etc. You don't have to go into the depth of it. Just the basics of it, understand. When there is compression, there will be a crack developed. One portion will start sliding over the other. They will start rising over the other. And that elevated portion, that is the reverse of tension, reverse of the gravitation. Hence, it is referred to as a reverse fault. Okay? Yes, most of the forces, Deepika, correct. Then we have graben. Graben is basically a combination of two forces, combination of two normal faults. Whenever you have two normal faults, so this is when tensional stresses. So let's say you have a large block here and you have a tensional force acting on both ends. There will be development of two cracks. Now, if the tensional forces keep on happening, the cracks will keep on developing. The cracks can deepen as well. Now, eventually, what will happen? They are pulled apart significantly. So what will happen to the central portion? There is nothing holding it together anymore. The central portion simply falls down, starts sliding down. That creates what is also referred to as a rift valley. Rift valley. Rift meaning what? Tension. India, Pakistan are experiencing a rift unlike ever before. Tension. So there's a tensional force creating a valley in the process. So that is what we regard as the Rift Valley. Okay? That is where, when we talk about River Narmada, River Damodar, River Tapi, most of them, they drain through rift valleys. So in central India, you will find these rift valleys in existence. Now, the opposite of the graben or rift valley in the sense, when you have development of two reverse faults. So let's say there is compression happening here. Or let's consider our own image. So let's suppose I have a rock like this. And I have a compression happening from both these sides. It can develop a kind of a crack. Simultaneous development of cracks might happen. These cracks might deepen significantly. And if I continue to compress, what will be the resultant of this? The central portion might get pushed up, right? Might get thrown up. So as a result of it, the central portion gets thrown up, creating what is referred to as a Horst, right? What is referred to as a Horst fault. Eventually, the winds will erode these top surface, creating mountain or peak-like features. This is what is also referred to as a block mountain. Block mountain. The lower portions of matter will come up. The lower portion of the crust in itself will fill it up. Ganesh. So that is how block mountains get created. Example, when you take a look at it, observe, this is how the host ends up getting created. This is how the graben eventually is created. So example, in India, you have Vindhyas and Satpura. Aravali's are a fold mountain. And then Vosges in Europe. So if I can dare to just give you that final portion before you are let go. So this is the portion, let's say Vindhyas. This is what is the Satpura. In between, you have a rift valley, and through that rift valley, you have the flow of river Narmada. Okay? All these are created due to forces acting from the interior of the earth. That is what creates all of it. Okay? So that is where we'll end the session here today. I will give you a kind of a map pointing if if you are on for it. So I'll give you a portion for map pointing as well. A couple of portions I want you to locate for maps. Yes, Ashwant, that is correct. So for maps, first of all, fold mountains. So locate Appalachians, then Rockies, then Cascade Ranges, then Brooks Range. It is in this Brooks Range that you will find the highest peak of North America. Okay? Or rather than fold mountains, let me just make it mountains. So here, then you have Sierra Madre, Oriental, and Occidental. Okay? All these, just to give you a hint, is in North America. Then Alps, Pyrenees, Carpathian, Ural, Scandinavian, Balkan. All these present in the region of Europe. Then Atlas. Where are Atlas Mountains situated? Yes, Kishan, that should be the approach. Atlas Mountains situated in the bordering areas of Africa, northwestern part of Africa, Andes. Okay, locate these and just locate as of now, locate these and look at the areas around it. Which are the areas around it? Tomorrow I'll give you more areas of map pointing. So we'll make it a periodic phenomena. Every 2 days I'll give you these. So when you take a look at the atlas, try to find it out where they are. Don't be restricted to that. Look at the vicinity areas also. Think about it, how they would have been created. Sierra Madre Oriental Occidental created purely because of volcanic eruption. Other of them, you can think about it. Cascade Ranges, youngest fold mountains of the world, formed very, very recently, or only around 1 to 2 million years back. So just take a look at it. Your information will increase. Okay. Now I'll take a few questions before I'll end the session. The map pointing you will get in the annotations. Okay. Uh, Honey has high density than water. Then why is it that honey flows slowly than water? So basically, it has got to do with viscosity. High density. So, for example, if you have molten iron will be dense, but it flows very easily. If you have, let's say, molten quartz, it will not flow very easily. So it depends on the viscosity, the ease of flow. That is the defining characteristic of it. Okay. So that is basically why when we talk about, see, mafic and felsic magma, Shalu, you had also asked a question about it. So when we say felsic magma is something which is formed at lower temperatures itself. Now here you might have question. Yes, you can leave the session. The class is now done. So felsic magma, when we say, it can be formed at lower temperature itself. Now, why at lower temperature? So across the entire region of lithosphere and asthenosphere, you have a variation in terms of material distribution, material density, which is present. As I told you, sometimes the materials will have a melting point which is very easily attainable. Sometimes it is not. So basically, the dependence on the type of materials which are distributed in various different areas, that contributes to the temperature required to melt them. Now, there you might have a question that how is it that we are going to determine in which area which kind of material is present? So there is a continuous mixture which is undertaken regularly with the help of convection current which are initiated from asthenosphere. There's a regular mixing up of materials across the lithospheric region. So that is why in certain places where you have a felsic eruption right now, maybe 20 million years, 40 million years later, you might have a kind of a mafic eruption in that region, provided the temperature in that region is high enough to melt the materials of iron and magnesium, because they will require a higher melting point. Okay. Shalu, does that answer your question also? And the question asked by Manish, both the questions, is it answered? Anjali, intrusive structures. Vindhyas is not an example of residual fold mountain. Vindhya is a block mountain. So when we talk about, okay, Anjali, intrusive structures solidified beneath the surface. So how we found it on the surface in the form of mountain or domes after the top surface has been eroded, weathered, dismembered, broken, then if you have a lot of layers above it, top layers are removed, what is left? The bottom layers. Okay. And Pulkit, how is it possible to have graben and horse simultaneously, since both of them are formed because of different reasons? Good question. So here, Pulkit, understand, if you have the presence of a host here, let's suppose, I hope you are able to see this. If you have a presence of a host here, now this is a kind of a low-lying area, right? Now let's say there's a simultaneous application and formation of another host in this region. So in comparison, this appears to be a graben, a low-lying region. So this is a very basic form, but many of the times what also ends up happening is that as you have multiple of these hosts which are getting created, so imagine a kind of a rock surface, if you can. Imagine a kind of a rock surface, very large, where you have compressional forces. So that is where, let's say, a crack has developed here, 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 and here. Now, as these forces will continue to act, this might get pushed up, this might get pushed up. Now, when these two areas get pushed up, what happens to the central portion? The central portion was being held by the surrounding regions. So, as the surrounding areas got pushed up, what will happen to the central area? It will simply start sinking. So that is where it forms a rift valley. That is the case around the region of river Narmada, the rift valley from which Narmada flows. Is that understood, Pulkit? Thanks, Alok, for the kind words. I just hope that the concepts are being understood by you guys. That is why I'm taking it very slow. Okay. And it is, first of all, it is not convention current, it is convection current. And convection current can be independent of mantle plumes. Some heat might be produced in a region, creating that convection current, let's say for 5,000 years and no further. Let's say for 2 million years and no further. So that is a convection current independent of mantle plume. Kishan, any significance of volcanoes in regards of minerals? So basically, the molten materials which are ejected, those molten materials, they spread out, they solidify to form those igneous rocks, and they will consist of many different minerals. Over a period of time, when the top portion is eroded, that is when the bottom portion that gets exposed, and that is where you can have the extraction of minerals. Okay. Mohammed, most probably by the end session of tomorrow or day after tomorrow is when we will initiate. Why decrease in pressure reduces melting point? Because as much as pressure is applied, the materials will require greater energy to free themselves from the bonds of each of the molecule. So if you release that pressure or the pressure which is applied, now even with lesser energy, they can get rid of the nearby molecules and get converted into liquid. So that is why with the release of pressure, melting point decreases. Okay. If we have multiple ups and downs, how will we know whether it is created by compression and compression or tension? Generally, when you have multiple ups and down, what is referred to as anticlinorium and synclinorium. So that is where, let's suppose it is like this. Generally, it is created as a result of compression from both ends. In which map will we get all these mappings? Open up the Atlas, Hariom. Look at each of these, North America, Europe, Africa. Look at these regions. You'll find these in the physical map. Physical map. Recumbent fold eventually, it is the asymmetrical fold which eventually end up creating a recumbent fold. Can a matter with low density have a high viscosity? Yes, silica, ideal example. Okay. So, do calderic lakes water is potable? So, not always, because in many of the cases, Surbi, you have seawater which gets in. So, not always. In certain cases, yes, when the groundwater seeps out. Graben is the subsided part, yes. Okay. Which type of volcano has lowest height? Lava domes, Priyanka. And then comes cinder cones, then comes the composite volcanoes, and then comes the shields. Right? Tomorrow we'll discuss multiple mains type questions. Sarita, you can start writing of those. All block mountains are horsed. Is it because of the felsic kind of magma that we do see the cinder cone? But sometimes even basaltic magma is there, but mostly felsic magma. In 15 mark geography question, try to get 7.5. Okay. So that is where I'll restrict the session for today. Hope it has been helpful to you guys. We meet again tomorrow. That will be the last portion of geomorphology before we transition into climatology. So thank you for the patient hearing. We meet again. Take care of yourself. Goodbye. Thank you.